So welcome everybody. Yes. This is a joint IT Technical Forum Computing seminar about automatic speech recognition and machine translation systems by UPV. UPV is the University Polytechnic, how do you say, Universitat Politécnica de Valencia.
That's right.
The speakers are Jaume Santamaría, Joan Albert Silvestre, Jorge Iranzo.
I'm Joan Albert, so there is...
So you are Joan Albert?
Joan Albert, yes, Joan Albert Silvestre, yes.
Okay. So I give you the floor.
Okay.
Your mic is okay.
Yes, my mic is on. So thank you, Ignacio. Thank you all to you for coming in. Also to the people which is remotely via webcast or on Zoom. And thank you very much for the invitation for giving this talk, in which we are going to summarize the work that we have done for the CERN, as the title says, for automatic domain adapted subtitling here at the CERN. Okay. Before starting, I would like to calibrate a little bit which are your expertise level on the machine learning field, just a bit. So I would like to ask first a question. Do you know which is the neural architecture, famous neural architecture that is behind, for instance, ChatGPT, this kind of large language models? Which one? Transformers, right. Yeah, you're right. Very good. We are going to talk a bit about transformers here. And do you know which is the name of the famous paper published in 2017 by Google Brain that presented this architecture? Yeah. Yes, more or less, yes. Do you recall the... Right, that's right. Attention is all you need. So attention is all you need here to have an idea of what we have done in the past 4 years, okay? And paraphrasing a bit this title, I think here at the CERN, subtitle is all you need, okay, to reach wider audiences, okay? So, okay, the talk won't be very technical, okay? We have prepared a very smooth and easy to follow talk in order to ensure that all you can comprehend and understand what we have done. Okay. Of course, if you have doubts or do you want more details, we can dig into. Okay. So first I'm going to, before starting. First, I'm going to give some context. Okay, for the work we have done. Okay, about the specific needs at the CERN. Also, who are we? Okay. We'll talk also about the projects and the collaboration we have done with you, the CERN. And we will talk also a bit about the architecture, system architecture that we have deployed here for this. Okay? And then I will let my colleague Jaume and also Jorge to talk a little bit in more depth about automatic speech recognition and machine translation technologies. Okay? So that's a little bit a summary of our outline. Okay? So, yeah, as you already know, the CERN is providing live streaming or live streaming collaboration services like now, okay? We are providing this talk via Zoom or via a webcast service provided by WOSA, right? Also, a lot of meetings, keynotes, and conferences are being recorded and stored and offered to the community, okay? And the CERN also produces clips on the video platform, like prepared clips for, to train workers and so on, okay? So all these kind of multimedia materials have a specific needs for accessibility for people with hearing disabilities, for instance. Also to lower language barriers, as you already know. The CERN is crowded by people from abroad, non-native speakers of English, also French, okay? So we have to deal with this, right? And also for indexation and searchability, because there are a lot a large amount of multimedia content generated every year here. So at certain point, it would be desirable to have a way in order to retrieve specific information that was produced in the past, okay? So a possible solution would be to generate accurate enough automatic subtitles for offline or recorded multimedia material, and also for streaming or live webcast and video conference meetings, okay? You have to bear in mind that the multimedia material produced here at the CERN is very specific. We call it a very narrow domain, okay? For instance, we have speakers of various nationalities with strong accents or non-native. Here we use terminology very specific from the high energy particle physics field, okay? And a very heterogeneous acoustic conditions, especially when people are giving talks or webcasts or whatever from their houses, from their devices, okay? But the key one is this, okay, the terminology, okay, the slangs that are used here in this particular field. So it's clear that a domain adapted solution, sorry, the pointer, it's very key in order to achieve accurate enough subtitles, okay? Regarding the production here at the CERN, this is like an estimation, okay? We did a few years in the past. So we had 30K hours of backlog data to be processed. Almost 2K hours, 2,000 hours of new multimedia content generated every year, and 1.3K hours of live video conferences or webcasts every year. So that's a very large amount of data to be processed. So given this context, it would be very desirable to have an on-premises solution in which we avoid variable costs related to the amount of data to be processed, okay? Because otherwise, it would be a too expensive solution for the CERN, okay? Also, it will be desirable to take advantage of, advantage of new data in the sense that we could exploit that data in order to improve the systems that are in charge of generating these subtitles, okay? So in 2020, our research group, MLP, was contacted in order to explore possible solutions. This contact came along the collaboration that already the CERN, the media service, has with the IT services of our university, the Universitat Politécnica de Valencia, regarding the Paella player that is used in OpenCast, okay? So the contact started there. Okay, so now let's talk a little bit about us, very briefly. So MLP stands for Machine Learning and Language Processing, okay? We are part of the Valencian Research Institute on Artificial Intelligence, and we are part of the Universitat Politécnica de Valencia. So we are not a private company, we are a public university, a public company, okay, doing research there. Indeed, we are 15 researchers, 5 lecturers, 2 postdocs, and 3 PhD students. The remaining 5 are undergraduate, okay? So yeah, I'm a lecturer at the university. I'm an associate professor. Okay, so yeah, that's the thing. And these are all research areas, main research areas: automatic speech recognition (ASR), speaker diarization, machine translation, speech translation, and text to speech. The most relevant ones for us are automatic speech recognition and machine translation. Okay.
Can you explain what is the diarization?
Diarization is to determine who spoke when in a multi-speaker recording. Okay, that's the area that tries to solve this problem. Okay. So here we have a brief short slide in which we highlight the most relevant research and development competitive projects that we have participated, the ones that have brought us the resources to develop our technology. So we have Translectures, EMMA, X5GON, and Interact Europe. So from 2011 to the current moment, okay? plus many other related European, Spanish, and Valencian projects. Okay. Also, technology transfer contracts. We have one with APUN, which is the local public television, and the CERN that you already know. Many other, for instance, the European Parliament, the Centre de Traducción Européen, Aptec, JSI, etc. Okay? Yeah, so a little bit about the areas in which we focus on. So automatic speech recognition, we have an internal software that we have developed in this last more than 10 years, okay? We support multiple languages. We have the ability of to adapt those systems, those models to the specific nature of each domain or organization. We have the ability to provide these services via cloud service, via an API or on an on-premise basis. Regarding competitions and challenges, we won on the 2018 and 2021 Radio Televisión Española Speech-to-Text Challenge. This is the public Spanish TV, okay? So they organize challenges for subtitling TV contents, and we won those editions, okay? We have some selected papers, okay, here, but I'm going to skip this for the sake of brevity. Regarding machine translation, we have simultaneous streaming machine translation technology, okay? We have competitive systems in European languages. Also regarding challenges, so we won the IWSLT 2022 speech-to-text translation competition and second place in the simultaneous speech translation. This is like the most important international conference on spoken language and translation, okay, yeah, so it's very remarkable. Some selected papers here, okay. This one marks the current state-of-the-art technology for simultaneous machine translation. We are very glad of it. And well, we also did a bit in the past text-to-speech. We had very competitive systems there, but our colleagues that were working on this left us to go to the private company. So. Yeah, just now a brief summary of the projects that we have done with the CERN, the contracts. So we had first a pilot project in 2020 for 5 months, very modest in budget, as you can see, but I think we cannot do so much in so little. So, so the idea here was to explore if we could apply these kind of technologies, automatic speech recognition, machine translation, successfully in the high energy particle physics domain. Okay, and yeah, the results were quite good. We had promising results on domain adaptation of these systems because we identified key data that will enable us to perform this domain adaptation. Okay. And we also defined some training and evaluation data sets for ASAR to objectively gauge the quality of these systems. Okay. Then, after this pilot project, the CERN was convinced that it would be feasible to seek for real solutions. Okay, to be deployed on premises here. So they issued a tender project to seek for for providers, technology providers, to solve these problems. No, and we applied for it. We finally we got it. This project ran for 30 months, from February 2022 to August 2024. Okay. The budget here was quite higher, of course, and because it was more ambitious. Okay, the idea was to develop an analog solution and deploy it here on demand, on premises. Sorry, to to integrate all these systems on the media workflows here. Develop domain adapted and for live subtitling systems for the CERN. Also another solution to integrate live subtitling into Zoom, and for the auto-training solution for continuous improvement of these systems with newly produced data. here at the CERN. Okay, so the results have been. We are going to dig a bit more in these particular results, but we have developed state-of-the-art in domain automatic speech recognition and machine translation systems. We have processed more than 30,000 hours of backlog data. We have a successful integration with Zoom, and we have developed an auto-training module that is capable to continuously adapt and improve the automatic speech recognition system in English that is here producing automatic subtitles. Okay. So you know that these systems, this technology is grounded on machine learning technologies. And talking about machine learning is talking about data. So machine learning models or systems learn from data to improve performance in a particular task or domain. So here it was very important to identify resources that could be useful for this domain adaptation, for this training of these models. So we identified first the CERN Opencast platform, which gathers an heterogeneous set of conferences and seminars, and from it we can highlight the LHCP recordings from the 2020 and 2022 LHCP conferences that were held virtually because of the pandemic, COVID-19 pandemic. Learning data sets or formative video tutorials for CERN workers, or the digital memory. Okay. And regarding text resources that are very important too, we identify the CERN document server, which are a huge amount of theses, scientific papers, and so on, and CERN News that contains CERN news published since 1993. Okay. Regarding the deployment of the solution, I'm going to give you a brief, like a picture, a broad picture of how we did the deployment of the solution here. Okay, so we have installed our software for deployment here on premises via virtual machines that are held on OpenStack. For the offline subtitling for recorded videos, we have installed the TLP, the Translators UPV platform, which is our own software that has been developed in the last 13 years. Okay, it features several components that are relevant: the database, the API, inter-service, front-end, and subtitle editor. I will talk a little bit of them in the next slides. For live streaming subtitling, the software TT Streaming, this is basically an RAPC API for subtitling live audio streams. And regarding ASR systems and MT systems, which combine software and models trained with data, we have for ASR the TLK and PyTLK, which are our own software, and FairSec from Meta platforms. For MT systems, we also use FairSec. Okay. Regarding the offline subtitling deployment, I have here two diagrams that are very abstract and illustrate just a bit how the deployment has been done. This box here is the TLP software, the main components, which is the subtitle editor, the player, the web service is the API, the inter-service is the component that processes the new medias and starts the process of generation of automatic subtitles, and the database that is also, of course, storing all the information. So the idea is that this client repository could be, let's say, the Opencast platform. So somebody records something, and this is recorded, and this is ingested to via our API. Okay. So this media package is processed by the ingest service, who calls the corresponding ASR or MT systems. You can think all these boxes like Docker images that do the whole thing. Okay. And then the resulting subtitles are stored in the database. So afterwards, users can watch these subtitles, or even they can post-edit these subtitles, because can contain some errors, of course. And these edited subtitles are stored, and then the ingest service, using the corrections, can regenerate automatic translations, for instance, because the source language has been updated, then we can regenerate the translations, corresponding translations. Okay. Regarding the streaming deployment, this is a quite vertical figure. I think you can't see barely anything. But I have a little zoom here. So we can think this about the IP users that wants to, one IP user maybe like this Zoom meeting, okay? This is the IP client. So it would like to live subtitle the current the current stream. So the idea is that the stream goes through the different ASR servers, MT servers, or even TTS servers for transcription, translation, or speech synthesis. And it can be a combination of all of them, because we can produce the whole pipe of speech-to-speech, like somebody is speaking in English and you want to hear him speaking in French, for instance, okay? So the idea is that this stream travels, for instance, there are already built pipes, for instance, pipelines for subtitling in English and text translated to French, or even speech dubbed in French, for instance, okay? And then these pipelines contact to actual raw ASR systems, MT systems, and text-to-speech systems that are hidden for the end users, okay? Because these are like building blocks to construct these pipelines that do perform some post-processing or, link different ASR, MT, or TTS components. Okay, this is more or less a peek that I wanted to show you. Finally, to end my part, we also prepared developed an auto-training module for build adapted systems that improve over time. Okay, so yeah, the idea was to automatically enhance the ASR systems on a regular basis, as I said, and to make them learn from these newly produced resources and materials. Okay. So in that way, the upgraded ASR models can know new or novel terminology that is being constantly generated here at the CERN because of the advances in the high energy particle physics field. Okay, so the main steps that we follow there are to gather and prepare new data, to train the model and assess the model, and to do some sanity checks, and finally to construct the upgraded system and its deployment. And all these three steps are done fully automatically without human intervention. So yeah, this is a scientific and engineering challenge, especially scientific because there are parts of this auto training that are not yet solved. Okay, we are let's say a bit pioneers in this sense, because it's a very difficult problem, but we have indeed a very good solution for that. Okay. So yeah, so for my part I'm done. So I'm letting Jaume to dig in a bit on the ASR part. Okay, on the speech recognition part. Jaume.
Yep. Okay. Good morning. I'm Jaume. First of all, ASR. The automatic speech recognition is the objective is to give an input audio. We try to obtain the verbatim transcription. The verbatim transcription is the one-to-one transcription of what it is said. Even if I repeat some word or I stay some time without saying anything, the idea is that the system obtains the best transcription possible. The first part, obviously, is to change the speech physical signal to a digital signal, so it can be processed for our systems. And in our case, we are following an hybrid approach. That is that the acoustic model and the language model are trained separately. Okay, they are independent models, and we combine them in the decoding part. So, well, the data that we use for all these ASR. First, we use the OpenCast. We crowd around 500 videos for a total of 430 hours. And we use this for training the acoustic model, for doing some domain adaptation. Then we use also the LSCP 2020 conference for evaluation set. So it is really important. I will speak about this later. And finally, the CERN document server, the CDS. We crawl around 500,000 documents to train some language model systems. And okay, the user has the main important metric is the word error rate, the WER. That is a measure of the incorrectly transcribed words or the edition distance between an hypothesis and a reference. It is calculated this way: have insertion, deletion, and substitutions, and the reference words is more like a score than a correct metric, because it could be more than 100% if we have infinite insertions, for example. And we have here a little example, just to understand this a little better. If the real phrase was GeV to TeV scale, feed particles, dark scalars, and dark photons, but our system just said GeV to TeV scale, particles, dark scalars, dark chocolate photons, well, we have 10 words in this segment. We have 3 errors, 1 of each type, and for a total of 30% of WER. By the way, maybe you noticed that chocolate is a fake. It's a fake error, yeah. And here we have some ranges in order to know how we can understand this WER better. We may have around 30% of WER. For a profitable for indexing and semantic representation, there are not high quality transcription. They are plentiful of errors. But when we have around 30%, it's starting to be good for subtitling. When we improve this word to only 10%, we have high quality transcription. And well, it's said that a word of only 5% is the human quality transcription. This is important to know that it's a human quality transcription for a professional transcriber in a domain that he understands. Well, we use all this technology for streaming, for live presentations, and we have some important challenges. First, that we are working with an unbounded speech signal. Okay? We're not working with a video of a concrete duration. So here we have a lot of problems. First, that we cannot process the full context of the signal. If we are speaking and there is the system has some doubt with some words, some concrete sentences in the minute 3, but the speech that can help this is in the minute 40, we know we cannot do this for streaming ASR, because we only have some small future window context, typically like half a second, and this is the only future context that we can see in each moment. So it's very complicated to work with this. It's also important to say that the real-time factor is usually used as metric for streaming systems. It's important that you know that a real-time factor that is less than 1 is a necessary but not sufficient condition for streaming. Because if we have a system that, for example, chops the signal in 8 or 10 small batches and process them in parallel, we can have a real-time factor that is less than 1, but if the average latency of each chunk of data is processed for a long period of time, the accumulated latency probably could be too much bigger that is not could not be reparated or solved by this real-time factor. So basically, we have a really important trade-off between the quality and the latency, and is the main challenge we have here. Okay, a few slides ago, I speak about LSP 2020. Well, yeah, we need a depth test evaluation and tuning partition, because if we are creating a domain-adapted system, but we don't have any set, any partition to evaluate its quality, it's not really useful, or it's not real, because we don't know if it's really understanding and learning the new words that we try. So with 5 CERN volunteers, we transcribed these 29 videos for a total duration of around 12 hours. Then they cross-review these videos following a concrete specific guidelines. And we obtained this verbatim speech evaluation set. Then we start by building a baseline system. For this, we use an acoustic model based on BLSTM DNNs that are recurrent neural networks. For this, we use 6K hours of transcribed general purpose data. ¿Vale? Okay, sorry. For the language model, we use an interpolation of a foreground. It's a count model, really simple, using 8 gigawords from general purpose text, and a more powerful neural model, a transformer language model, using only a subset of the words of 1 gigawords. This system scored 24 were in the LSCP 2020 test. So we can see that this model is really it's not very powerful for this domain. So we need to build something better. So for this reason, we start by adapting the language model, because the language model is the part that learns new words. So we replace the general purpose transformer model with an updated one that uses 1 gigawords of in-domain content published for the 2020. This is the data from the CDS. This model has a closed vocabulary of 250 keywords. This is important to note that this is a closed vocabulary. If there is a spoken a new word that is not here, the system will not recognize it. This is typically can be seen with new names for people and so on. But with this adaptation, we achieve an improvement of 90% respect the baseline system. We're starting to get good metrics, but we can't stop here. So we adapt the acoustic model system. We fine-tuned the acoustic model. This is we continued the training from the last point from which it was training, using, in this case, the data from the OpenCast that we prepared. And using the system, we have an improvement of 17% regards to the previous system, not from the first. This system is really good. So we use this system to pseudo-labeling around 12K hours of in-domain videos of OpenCast. Yeah, from these 12K hours, we start a filtering process based on phoneme length heuristics. This is to see, to discard the videos that has less than some percentage of transcribed data, or that have some problems, maybe are corrupted, maybe are not in the correct language, some of these problems. So the total amount of data was reduced to only 9K hours of in-domain speech. Well, only. So we use this new data that was with a high quality transcription to create a new acoustic model. So with this data, we trained an acoustic model, but in this case, using a conformer architecture. The conformer is a transformer, but grabs some ideas from convolutional layers and so on. In our case, for this work, it goes really well. We achieved this really good metrics here in the test set for a total cumulative improvement of 43%. Sorry, obviously. We use the same language model that in the previous systems. Yeah, so we create a new evaluation task just to double check this quality through time. This will be important for the part of auto-training. So we grab 43 videos from plenary talks for a total of 80 hours. Well, in this time we manually transcribe, just 8 of us. It's important to note that we are not experts, we are not transcribers, nor physicians, so it was a bit challenging. In order to have to ensure good quality, we use the same guidelines as in the previous partition, but with a new role. There are moments in which we doesn't understand because it's a very technical jargon or because the audio quality was not enough good. So in these moments we use the ANC token just to clarify that we don't know what is spoken in this concrete word. Yeah, it's important to know that in this case we have a relative factor of approximately 8 points. That is, for a video of 1 hour, we were reviewing this video for 8 hours. That is around 3 times more than the times expected. It was really heavy task. But yeah, we obtained this really good data set. We try to manage the partition from dev and test using the previous system to have an equilibrate difficulty. Okay. And then we try to compare our models with the ones from OpenAI. OpenAI is the same company as that built ChatGPT and so on. Whisper is a model that was trained with a crazy amount of data, 680K hours of general purpose data. That is important. And we tried two models. The medium one that has this amount of parameters, and the turbo. That is a large model, but optimized to work really faster. And our fully adapted system that I presented just now. We can see that our model is still really small in comparison. But yeah, we can see that even in these cases, we have a really good improvement. This is principally because our system is adapted to the domain. This is something that obviously big companies cannot do for every domain. That is, and unless you pay like really a lot of money, but it's not part of the important things that they do. So yeah, it's a pleasure to say that we are releasing this data set. We were talking while this contract is still on, so we released this data set as a paper, okay, that describes, first of all, the creation and provides references for both partitions. Yeah, with these 2 evaluation partitions, LACP 2020 and 2022, for a total of 30 hours of verbatim data. We used the remaining data from the LACP conferences from 2020 to 2022, that are the ones that are recorded, for training or adaptation of the systems. And we submit this paper to Interspeech of this year. is one, for context, is one of the most important, if not the most important, congress in this field. So we are very excited about this. And yeah, we do this yesterday. It's the last day. And well, we are very proud of it. Okay, about the auto-training steps. Whoops. First of all, we create a delta dataset from the CDS and the CERN news. From this, we extract and clean this text data. Then we build a data partition, and it's when we start to extend the vocabulary of the transformer, the language model. It's important to note that for the auto-training steps, we are not updating the acoustic model, because the acoustic data is very strange, that will vary from the used 9,000 hours. But there could be new words as physics are changing. There are new theorems, there are new ideas, and it's something that is important to change. This is okay, and then we made a sanity check, just to check that everything is okay and we didn't break the system. And finally, we do the system tokenization and deployment. Okay, for the data acquisition, we obtain the data from the CDS and the CERN news. We have specific crawlers for both data sources. They have its own structure. Yeah, well, it's only important that say that it is all automatically from a given period. And we have a minimum threshold of data because if there is small data, we cannot improve anything, so it's not usable for anything. As experimental setup, we use as a baseline system the one that was trained with data until June 2020. We have an update system using data with this delta time. Okay, and finally we create a new delta dataset of only 5 months. From January 2024 to May, we create these subsets. Important. We have different metrics here. We have the OOVs. There are the out-of-vocabulary words, the words that are not present in the vocabulary, so will be never recognized by our system. So they are a base error that we are assuming. Okay, we have the perplexity of the language model. We can see this here, and we can understand it as the amount of words that could follow a previous history. Okay, for example, for all the speech that I've done until here, the system probably say we can use around this amount of words, 190. For the updated system, 85, and for the auto-trained only 72. So we can see that using the new delta dataset, the systems are slightly better as we are auto-training these systems. Yeah. We can see also how in the LHCP 2020, these data, the models are slightly degrades because, well, the language models are based to the future, but we can see that this degradation is slightly small, so it's acceptable, it's totally okay. Well, the where is only compute as a sanity checking, just in case that the where goes to 30 or 40, we say, okay, this is something that is not working well. Well, for something completely different, Jorge?
Okay, you can hear me? Yes. So we don't have much time, but I will go briefly, or well, not so briefly, regarding our empty systems that we deploy here at CERN. So our empty systems mainly consisted in two types of systems. One for the offline tasks, for offline documents, textual documents, and another task for live translation. Okay, so I will give you now a quick overview for the data sets that we utilized, how we did the automatic evaluation, the system description, and the experimental results for both the offline and the online or simultaneous machine translation case. Okay, so first of all, how we did the evaluation, we created two kinds of evaluation sets. First of all, in the CERN news domains, so we extracted English and French translation pairs from the official website, from a various array of topics that I am sure that you are very familiar with. Then we also extracted from various theses from here at CERN, with this data set being a little bit harder, with more technical vocabulary, and also a lot of mathematical expressions. This is also for evaluation, and also we extracted some translation pairs for training. In terms of data sizes, from around 1K to 2K of sentence pairs we evaluated, which is typical in the machine translation literature. Okay, so about the evaluation process, we mainly relied on automatic evaluation. This is very typical because human evaluation is quite expensive. It is not trivial to go around and contract a few people to translate. So manually in this process, we just simply get a score from a metric. Automatic evaluation is actually a very hard task and quite an open task. This is an example like, okay, so how do we know if Auto 1 and Auto 2 with respect to this reference is the better translation? You know, which scores we can have so we can then say that system A or system B is better. We mainly relied on the bilingual evaluation understudy metric. This is quite a widely used metric. There are newer metrics that also rely on LLMs and stuff, but we mainly rely on BLE. We found it quite still a robust metric. I will not go into details, but it mostly measures the degree of overlap between a machine translation hypothesis and then a human translation reference. To get a better idea, around scores of 40 BLE in the English and French translation pairs is traditionally considered translations of good quality. Okay, regarding the systems, so we train encoder-decoder transformers from scratch with quite a good amount of data. I think it was around 300K or 400K sentence pairs, if I remember correctly, on top of my head. We train two systems, a more efficient and smaller one, and then a scale one, which had 3.3 billion parameters and 3.6 parameters. To get a bit into perspective, for example, Llama 3, which is a widely used LLM, has around 7 billion, and even more bigger models, for example, GPT-3, it is 175 billion parameters. So these are quite small models, quite efficient models that also are very good because then we can use it for live translation. Okay, so we did train these models, and also as a baseline, we compare with NLLB, No Language Left Behind, which is a multilingual model released by Meta, which is a couple of years old, but it's quite still the state of the art. Okay, so here's a brief table of the results, but as you can see, you know, bigger is better, and in our case, our systems, or bilingual systems, are better. Also, I didn't mention it, but these systems also what we did to have the terminology, in the CERN terminology, is that we extracted monolingual data, monolingual French data, and then we trained a reverse translation model so that then we had the translation pairs. So we created synthetic pairs with the English part being synthetic. Okay, and as you can see, the NLP models are actually quite good, but as you can see, like to get the same level of translation quality, you need a 3.3 billion model, and then we just need a 3.3 or 3.6. This also has some couple of tricks under the sleeve, the 12-layer model. So yeah, it works quite well in both domains, as you can see, with 40.2 and 40.3 in the case of news and thesis. Okay, so this is for the offline part. Now we will go to the more, at least for me, because it's my research topic. But this is the how do we take this offline system, machine translation system, and how do we combine it with the ESR to obtain a simultaneous speech translation that works on a live stream? You can think that this task can be a little trivial, but actually it's quite complicated. Like, you need to be very careful in the way that you design your model so that it just doesn't break and fall apart. For example, here's a couple of list of challenges, but there are plenty of more. One of the most obvious things is that the ESR output can have a lot of transcription errors. So you need to be very careful with the emission frequency of the ESR model, because you just can't wait a lot of time and then be sure that your ESR model has a very good quality, because then you have a very high amount of latency, and then also the MT system has to process. Also, the MT systems needs to translate on the fly. It cannot wait for full sentences. Ideally, we would wait, but we cannot do that, because then we have maybe like a latency of 8 seconds. You wait 8 or 10 seconds for a translation that says hello, and it says bonjour, and you say, okay, this is not a live translation system. And also, you need to be able to have a system that doesn't accumulate delays, because maybe it is simultaneous with a video of 1 minute, but then if we go to a talk like this, that maybe it's an hour, you need to be very careful. Okay, so in terms of evaluation, we can do the translation evaluation, but we also need to take into account the latency. I will not go into details. The questions are a little bit complicated and hard to explain, but the gist of it is that we evaluated with average lagging, which kind of measures the number of words that a translation is behind the source. And then also we measure the translation lag that actually measures the real time elapse between the utterance and translation. You need to obtain some alignments with the source and target, but I will not go into details. For evaluation datasets, this was a limitation that we had, is that we didn't have a dataset that had both the CERN domain and it was for video streams. So what we simply did is did the evaluation on academic benchmarks that also are quite good and robust. Europarlist, which is made of debates from the European Parliament, and also MAST, which is from TED Talks. Okay, in terms of the system, actually what we did is kept kind of things simple, or to be more accurate is to how do we take our offline architecture and adapt it to the streaming scenario. People in the literature like to complicate things, but we thought that it is not really necessary to get a very good and robust system for live translation, streaming translation. So a couple of things that, for example, that we did is, first of all, in terms of not in the architecture, because it's mostly the encoder-decoder transformer of the offline case, but modified the training so that then we can take the outputs from the system and then depending on what it is output, we can control the way that the stream is processed. For example, well, the first thing that we did is practice training, which is just simply utilized the training samples so that the system is able to translate incomplete sentences, because mostly you train with the whole sentence, but this leaves a system that is quite unstable. It cannot translate, this is typically what is done in the lecture called prefix training. And then this is quite the most interesting part, is what we did is we designed our models to be context aware and to have a history cache of the whole translation input. Because in typical simultaneous empty systems, like people translate sentence to sentence, and they do not take into account past information. And what we found is that in practice, it is really important. Like you can get up like 5 or 6 points of delay just like having a small sentence cache of like 3 sentences. Also, because we had a cache, then we designed a little bit of a clever mechanism, which we made our system so that it learns to emit like a control token, which is called here the SEP. And when our system generates this token, then we can call an external system, which actually the fun part is that it can also be the same translation system. And then we can look at the stream and say, okay, so maybe this part of the source stream has already been translated. So we can just move it to the translation cache, and it's maybe if it's a really old segment, we can throw it out. Okay. Also, we did some things with the with the word emission policy, because we also need to control things. This was recently published in the ACL, and we got quite good reviews. So yeah. Okay, very briefly, just some results. You need to take into account this, the trade-off between latency and translation. In the case of the CERN, it's mostly like here, these models that have like very good delay, around 40, and the latency, which is like 2.5 and 3 of TL. To put things into perspective, the ear voice span, which is like the typical measure of interpreters, typical mean ear voice span is around from 3 to 10 seconds, depending on the language pair. So this is quite usable, and it works. I can say that it works quite well. Okay, so this is the translation and speech translation systems that we deploy, and now I will pass it to my colleague Jorge for the closing remarks.
Okay, only just one slide because we are already late. Just to remark some issues of this, some points of this talk, of this work over the fall last year. Well, as you know, we are now providing offline and live automatic subtitles to CERN. I mean, I invite you to use it. I mean, actively. You have the opportunity to have a state-of-the-art in-domain ASR and MT systems deployed at CERN, providing very good results. And this has been possible mostly thank you to the close collaboration with CERN IT, with Ruben, René, Pedro. I mean, all these guys that allowed us to deploy an on-premise installation. So this is very convenient. They have already transcribed more than 30,000 hours of videos that are now available and indexed. Okay, well, as I have already said, we are going to release a new dataset, the LHCP dataset. It's upcoming in this paper that Jaume mentioned. And finally, you have also the opportunity to be independent, because you can train your own system over time, so you can improve your own system with the new terminology. So this is all. I would like also to thank now here to Ruben and all the IT team, Pedro and René that were involved in the project for all these 4 years. It has been a very good collaboration. It was a very good team. And also I would like to thank my team for all this work, Joan Albert, Jorge, Jaume, and also Gerard, Gonzalo, and all the people that is also in Valencia. So I would like to thank them for this work. Okay, so hope you can enjoy now these systems and you make the most of them. Okay, thank you very much for your time.
And many thanks to the speakers for the excellent presentation. If there's any question or comments, Manuel, please use the mic.
Thank you very much. I mean, you are doing much more with LLMs than we do at CERN, generally speaking. We are not so much in this business of fine-tuning LLMs. I was thinking that, in the future, we plan to use LLMs for various purposes. And for instance, one of the purposes could be summarization. I understand that the data sets that you are used to train your models, they are open source, which means that, for instance, if a model that we want to use for summarization, we want to fine-tune it so that it knows about the CERN jargon, so then we will be able to use your data sets.
Yes, I mean, all the data that we use now, for example, for CERN, all the data was, it's the CERN that you have available. For example, from CERN document server, we are using this data, and also the OpenCast data, all this data. All these systems have been trained with public data. Yeah. So you can.
And the data sets themselves, they are available to anyone.
Yeah, I guess yes. I guess when all the data sets from CERN, I think they are available. I think maybe.
Yeah. Just now. Only the part that is stated here is what is being released publicly as a corpus, but of course in the CERN document server or maybe in the Indico platform, you can grab some medias from there. Okay, but just to be released publicly, we have permission to release this data. Okay, just this data and nothing else.
Okay, and then the models that you have build yourself, they are open source models? I mean, they are available in Hugging Face? Or?
No. These models are just for the CERN, not open. And even if they were open in the part of ASR, they would need the software or our software TLK that it's not open. This software is internal for the university. It's a registered software, but it's not. It has not a public release.
It would be very nice if there would be an open source LLM that will be equivalent to the OpenAI.
Well, the LLM, the language model part is based on, in this case, on FAIRSEC. FAIRSEC is an open source software. Okay, so that's not the problem. But the thing is that the models that we have developed are internal for the CERN. But in any case, as the data, our LLMs were trained on a subset of this, 1 billion words. This is 1.5 billion words. So anybody can train a language model with this data using standard receipts with FAIRSEC. So, yeah.
Thanks. There was a question over there, please.
Thanks. I have a question. Am I got correctly that this speech recognition system automatically detects the language the users are speaking, or you need to press select?
No. In our case, it was precisely done for English and for French. But we don't know. We have done it in the past for the application, for example, when we perform this pilot for the European Parliament. We ran some tests to detect the language. We were running several systems at the same time, and depending on the system with the highest probability, we decided to use this system. But in this case, you have the French system, you have the English system, and you have to decide which one you want to use.
Yeah, I'm just referring because some of our meetings, they are actually can be switched from English to French and the back. So it would be interesting to have some kind of automated switch automated detection and automated translation.
Yeah, sure. It would be nice to have a bilingual, for instance, multilingual ASR system, but in our case, we follow the monolingual approach because we focus only on English. We also developed the French system because, for having it, because there are also people speaking French here, but most data is produced in English, so we focused on, let's say, giving the best of our efforts to build the better system for English. Yeah.
Yeah, but as you say, it's a very interesting problem, and the problem in which you have speakers speaking the different language in the same room. Indeed, Joan Albert, maybe he doesn't remember, but in Apunt, in this local TV, we have that problem. We have Catalan and Spanish people speaking at the same time, in the same dialogue. So it's a challenging problem, and that we are facing now. We hope to be facing now in the following contract that we will expect to have with the local TV, because this is a real problem that we have every day. Yeah.
And maybe question not to you, but related. Is there any documentation how to use it here?
I mean, we have you can sign for the service, and you can get an account, and you can use the service using a REST API or via the web interface. Yeah, this is visible. The service is called Transcription Translation as a Service, titas.web or .docs, depending if you want to go to the docs or to the web UI. Yeah, but you can contact us anyway.
Thanks. Pedro, please.
Yeah, first of all, thanks a lot for the great presentation. So it was really interesting to see a little bit, what's behind the scenes. And also to reiterate what you've said, it was a really nice collaboration. And it's something which is already available, actually. If you look into the technical forum of last week, for instance, the subtitles are already there, and also the French translation. So I wanted to ask, first, I have two questions, actually. The first one is, I don't know if you wrote it somewhere in the presentation, maybe I missed it, but how many hours of training did this were spent in this model? I mean...
In our adapted model?
Yeah.
9,000 hours.
9,000, okay.
Of in-domain data, yes.
No, but not data of GPU time.
GPU time.
GPU
computing resources.
2 to 3 weeks.
Yeah.
2 to 3 weeks.
Okay. 2 or 3 weeks, yeah.
And then the second one is, I've seen there are some players in this area of ASR and so on who are now using LLMs as kind of a post-processing step to kind of fix some mistakes in the transcription based on some, on some prompt or embedding or whatever that is provided as context. Are you looking into something like this? Is this something that you already take into account? I mean, are you aware of these? Well, I'm sure you're aware of these techniques, but how do you rate them against these?
This is in the stake of ideas that we are willing to try, no? In order to we are using hybrid ASR systems, and one of the main components is the language model. So we are using a small language model, but nothing prevents us to use a large language model, and indeed. Also, we can also use a fine-tuned large language model for this task, particularly. So that's something that we will we plan to explore in the next months. Yes, for sure. Thank you.
Please, Chris.
You earlier mentioned, the second talker mentioned a score of 5, which is like comparable to like a professional dolmetscher, and the score of the automatic one was 13 point something. What is that comparable to?
This one, right?
Yes. And the score of the automatic one was 13 point something. What would that be like comparable to?
Sorry, say again. The microphone is...
sorry. The final score was 13 point something. What is that comparable to?
I don't know.
I mean the 13 that we obtained, that we reported.
The best result.
How it compares? I mean, this 13.
This 13, yes.
How is it relates to
good quality transcriptions? Yeah.
I think it's very good
usable, near to high quality transcriptions, but this word error rate, also if we compare it with OpenAI's whisper models, which are state-of-the-art general purpose systems, it indicates that we are facing a really challenging task. It is not like other popular benchmarks in ASR like LibreSpeech or Tellium that reach word error rates below 5. These are tasks that are already solved by the current technology. But LHCP, it's a really hard task that is not yet solved. So that's why we also are releasing this corpus, this paper that we sent yesterday with the release of the data, because ASR field needs new challenges, new tasks that are really a challenge for the technology in order to, to stimulate the research, pure research on ASR. So that's the key here. It was very interesting for us to work with your case, right? So
I think what they achieve is really good for an automated. To qualify it is very good for an automated system. The thing is that the 5% there is for a professional. Well, I'm pretty sure that I would not achieve the 5%. You see what I mean? You need to know the domain and be a professional guy, able to keep track with that.
Yeah, I think indeed, Ruben told us your experience with the professional transcribers, that after a few minutes, like listening to the LHCP talks, when he was saturated, he couldn't keep transcribing because the terminology was so different from what he's used to transcribe that he couldn't keep the pace with the speakers. So, in this case, what you have is that, especially this difference is mostly different from the terminology. The terminology, because Whisper are general purpose system that we work very well with general talks. But when you go into in-domain or, like in this case, or specific terminology, it makes a real difference. And this is our strong point, our capability of training in-domain systems for a specific domain. This is the
Yeah, no, we can. Oh.
You can talk here if you.
It's important to say that these systems are streaming systems. Whisper is an offline system, and it's important to say that one of the problems of the word metric is that I forgot to say, sorry, it's a binary error. If the word is, for example, professor, and the correct word is professors, it's an error, but it's perfectly understandable. And it's important that the references in this case are reviewed and corrected by us. So maybe there are some error with some technical words, and probably the system will outperform us. So maybe part of the error is not an error, but the errors are ours.
But it has a very limited impact because these tokens that we put in the transcriptions are less than 0.5% of the total token, so it's really not an issue that. And yes, just like he said, Whisper models are not streaming capable, but ours, yes. That's the another difference that we haven't stated there. Maybe we ended these slides yesterday at 2 a.m., so maybe we were not fresh to put this. But,
yeah, and the same happened with the translation. Translation and streaming, the capability of having speech translation and in streaming with a low latency as you have now here at CERN is just was published last year, and now you have deployed here at CERN and you can enjoy it. So it's basically, this is also a strong point from us. It's the capability of offering this technology in streaming. This is also, I would like to remark this point. Yeah.
And I also wanted to remark regarding the LHCP data that this 8.1 real-time factor. This is that it took 8 hours to review. To post-edit 1 hour, because we used a transcription generated by automatic transcription generated by this system with this quality, which is quite good, okay? But this indicates, this high real-time factor indicates that this task is really, really hard even for a human transcriber. You know, because the literature says that for this amount of error, okay, we should have around a 4 real-time factor revision effort, around 4, and it took for us 8. Maybe it can be influenced by the fact that we are not experts, maybe, but as a transcriber, as a reviewer, I can assure you that it's very hard to understand correctly what is being said because of the acoustic conditions, because the strong accents, and it's not fully related on the jargon, on the terminology, okay? So that's why this data set, we believe will have a very big impact in the ASR field.
Thanks, Herman, please.
Yeah, maybe precisely a follow-up question on what you were saying. I mean, on the impact. You're saying, I mean, this is very specific domain language field for which you have specialized the model. And then you have the very particular accents we have here. How much of all this will be useful for you for feeding into your generic models, if anything?
How much, sorry, say again, how much what?
I mean, what of your learnings you have obtained by building this domain-specific model, are you able to feed back into your generic models?
Okay, let me see the slides, the evolution of errors that we have here. Okay, first of all, this is the, okay, sorry, I can see, sorry. This is the baseline system. This is the baseline system that we have. So when we adapted to the terminology, this is the decrease in error rate, just because of the terminology. When we adapt with a small amount of data from acoustic data from CERN, 400, we just decrease to this value. But when we were learning from the 9,000 hours of this was, I mean, unsupervised data. It was pseudo labels. I mean, it was automatic transcription that was used to train our system, but we were taking into account that we were using the acoustic condition from CERN, the accents, the acoustic condition, the reverberation of the room. This was decreasing from this value that was already adapted to the acoustics down to this value. Of course, we now were changing the architecture, but we also were taking into account that we were using an order of magnitude more data in the acoustics, but only from CERN. So we were adapting so I think it was only training with this.
So we went from 6,000 hours of out-of-domain data plus 400 hours of in-domain data, fine-tuned, okay, to 9,000 hours only of in-domain data, but pseudo-labeled with automatic transcriptions that may contain errors. The acoustic model learns from that, from 9,000 of hours of speech data that may contain some errors, an error that is estimated on this error rate, approximately. And even that, we reached a huge amount of relative improvement. It's like 15% or so relative. So that's what the acoustic data conveyed from here to here and from here to here.
Right. So what you're saying is that your generic models will benefit of the work you have been doing with CERN.
Yeah, the generic models are benefiting, hugely benefiting from this data that are being produced. So the case is clear here because we just relied on data that was subtitled automatically by the systems that were already deployed on production on the CERN.
Okay.
Yeah, thank you.
Yeah. Okay.
Jorge.
In this case, this was a system fine-tuned. We took our acoustic model and we fine-tuned it with the acoustic condition from CERN. And this system was the acoustic model of this system was trained from scratch only with the acoustic conditions of CERN, but with using unsupervised data, with automatic transcriptions. So this was fine-tuned with a few hours, and this was only trained with acoustic conditions from CERN. Even these results were using only automatic transcription that may contain errors, and this was with good data. So in general, the general message is more data, it makes the difference, even if you have automatic data, automatic pseudo-label data.
I think that actually he was asking another question. So I think that you were more asking about like if you use this data to train a general purpose model, like is it useful? Was it something more like that?
Well, twofold. Is the data itself useful, and the learnings you have applied by changing the model?
So it is useful because more data, better models, and also the fact that if it's like hard data, a model that is able to learn from the data indicates a good model, because if it's the data is harder and the model doesn't learn that hard data, well, then you don't have a good model, So we really need like these data sets to also train general purpose,
Yeah, my comment was originated by the fact that you can easily overtrain maybe a model by just injecting too much domain-specific data.
It's a very hard balance.
Exactly, and then suddenly your generic model doesn't work that well any longer. You see what I mean?
Thank you.
Thanks. Manuel has another question.
Final question. For the transcription, for your transcription model, have you compared it with commercial solutions like DeepGram?
Like what? Which one?
DeepGram?
No, just DeepGram. We know DeepGram, but no, we just compare with Whisper, only Whisper.
Okay.
Because our commercial, you have to pay tokens. We didn't.
I mean, you compare with No Language Left Behind. I mean, it's the translation, I think.
Well, no Language Left Behind is translation, but it's open.
DeepGram is for transcription.
Yeah,
voice to text.
Yeah, I think the difference wasn't that big with DeepGram. At least the last time
we did a comparison. I mean,
but I think
2020.
I think that we didn't check up like formally DeepGram, but myself, I saw like the results that they have, and I think there wasn't like a big difference. But it was another data set, so maybe like in HCP the results will be different. But I don't think that probably DeepGram has the access to certain data that I know of. That will be quite problematic if they somehow have access to your servers. But,
But I don't think DeepGram models would beat the performance we achieved there. It could be, of course, but if I would bet on something, I would bet not.
Yeah. Yeah, I mean, the thing is that I do not know these commercial models if they offer the possibility of enriching their models with data that is specific to a given organization, like the acronyms of CERN and this kind of things.
Yeah, maybe I think they offer that. I think they have the line for that.
at least as an as an easy to use service, I don't think that most, at least ASR companies do. I know that LLMs companies, like for example for an OpenAI, you can do like your own ChatGPT and do like if you have some data and then train like something like a LoRa or some other adaptation technique. But at least in the case of ASR companies, no that I know of. Probably like if you contact with them, and you say, okay, so we have this data, can you please train us these ASR models and we pay you a lot of money? You probably do.
Yeah, it's something that is not open to the big public, but for special customers, they probably can do that.
Yeah,
this adaptation.
The thing is that apparently out there are companies that they sell kind of chatbots, but where the user can use them verbally, and there are many of them which are using DeepGram for the transcription to text.
Mm-hmm. Okay, so we will have a look to DeepGram in that sense.
Please, Ruben.
I mean, as you mentioned there was a couple of the data sets that now, when you use the actual techniques, you get like a 5% of work. I mean, you have an expectation with, in domain like us, with this particular jargon, how long it will take to, to the technology to get it into this professional wear? I mean, it's just your expectation.
I don't know. I think it will come with data, more data. And as soon as we have a big model that has a lot of data, including this in-domain data, we'll finally be reaching this kind of words. But maybe less than 10% is possible, but achieving human quality, this wear of 5, I think it will be difficult because of the intrinsic difficulty of the task. Because for us, as humans, I think we are better than an automatic system. It was very, very, very hard to have complete verbatim and correct transcription. So we'll see. I don't see automatic systems reaching these words below 5 and so on, like in Libre Speech or Teleum. I don't think so. Below 10, yeah, probably, but not below 5.
Regarding I'm sorry, just to add to the answer, regarding the 5% figure, maybe we didn't mention that a professional transcriber that gets under 5%, this person does not work in real time.
Oh, yeah.
You don't get real-time subtitles under 5%. Yeah? This system is getting 13% in real time. When you have real-time subtitles on TVs and so on, it used to be that someone was typing that in real time, sometimes in turns, several people, but you didn't get 5% error rate. I mean, in real time transcribing, you get higher error rates.
Possible.
So maybe 13% means that these subtitles are useful to follow what is being said. They might mislead you at some points if you are totally relying in the written word, yeah? But they are useful, and we expect them to improve. We don't know if as low as 5% for a really challenging task like this, but we're still talking that this is real time, so these are very good results and they are useful as they are. Yeah.
Thanks, please.
Yeah, one more question. You've barely touched the text-to-speech system. So is the automated voiceover something foreseen, or it's... and also for the automated voiceover, I have a question. I've seen, like, from the user perspective, how the automated subtitles are working. So they are constantly, like, can go back in time and correct themselves at some point. And so how the voiceover system is working with this? So you just add delay, or so?
Yes, they work with at least with the delay that the machine translation system is giving. That it's like 2.53 seconds plus the delay of the streaming ASR system, that it's around 1 second, a little bit less, maybe 0.9, 0.8. So you have a lag for the doubled, cloned doubled voice of around 4 seconds, 3-4 seconds. Yeah.
This is actually a very interesting question that you ask. Actually, that's the problem of of flickering, no? The flickering of the translation system, and then how do you control it so that your empty system doesn't have a lot of flickering, because then it's going to pass to the TTS, So the thing is that you cannot wait a lot of time.
Yeah, when you have a flickering system, as you mentioned, that is changing the translation as it goes, you cannot use it for TTS because it's going to be changing. You cannot change. In this case, we are not changing. Once we generate the translation, this is fixed. So it could be used for TTS. It could be used for TTS in streaming. It depends on the system that you use for streaming. But in our case, it's not. This effect doesn't happen in our case. Yeah.
Thanks. Any more questions, Manuel? Comments?
I had a final question. You have done a great work in the last 4 or 5 years, no? And this is excellent. I like it a lot. But now, the thing is that in the last 2 years, a lot of things had happened in terms of available models and all this. So what are the things that you would change if you have to do the same thing that you have done, but starting now?
Yeah, I mean, when you have a flickering system, as you mentioned, that is changing the translation as it goes. You cannot change. In this case, we are not changing. We are not changing. Yeah.
Bigger models, more data. Bigger models and more data.
No, for example, Joan Albert was already mentioning that now the opportunity is you can replace your language model in our ASR system by a large language model. And it's for sure that is going to improve. If you take a large language model and you fine-tune with the data coming from CERN, it's going to, that's where already I am quite sure that it's going to decrease, because you have a large coverage from the large language model, and also you have the opportunity to fine-tune your model with in-domain data. So that's a possible way of improving the system. Yeah. And already in translation, in machine translation, we are already working on taking this large language model and also pre-trained. Indeed, we have already tried a no language left behind system and convert it into an streaming system, and it works. It doesn't work as well as the one that we have, but you can convert, and you can train these systems to be working in a streaming mode. You can fine-tune the model to make it work as a streaming system. So it's possible to take advantage of large language model as no language left behind and make it streaming.
Yeah, you can even use bigger models.
Incluso.
There are some early experiments taking Llama and DeepSeek, and they work
Jorge is working on that area.
To do a little bit of things to make them work, but it can be an interesting model.
Jorge is working on that area, on the idea of taking a large language model and make it work in streaming, as a streaming. It's an interesting open problem. Yeah.
I mean, I just wanted to add on that I see also some trend that people it's not real time, because they introduce a delay that can be even till 3 minutes, but then they are using bigger models behind because they can afford it. And if you also control the streaming, you can play around that, lower your expectations on a model that is so capable to respond in low latency, and then have something that is more powerful behind doing the transcription translation, because you can delay the stream itself. Mm-hmm. So I mean, just the mention.
Hello. Yeah. Here it's important to note that there is another problem, and it's all these systems work on user graphics. I mean,
they are consumer-grade GPUs.
Yeah.
We don't have a lot of computing power, unfortunately. So for these big, more recent models, you need quite beefy GPUs to use. Like things like Llama and DeepSeek are quite heavy in terms of VRAM usage. So this is also a very important point that, everyone's like, let's use LLMs. If you have the money, of course. If you don't have the money, you cannot use them.
Yeah, just to say that regarding GPUs, the last system or best performing system was trained during 3 weeks, but it used just one GPU, a powerful one, which was an A100, no? A100, yes. We didn't use a multi-cluster GPU, no, just one single GPU. Took 2-3 weeks, and that's it. So, yeah, I mean, it's not very expensive, the training of this model. It's a small model, indeed, with just a bunch of data in comparison with big models that, Google is training with more than 1 million hours and so on. So we cannot afford that.
Just to mention that also the actual model that we are using in ASR is a model that we trained using the system. I mean, a small delta, but it took like 10 hours to produce it. So it depends as well, how long is your time period and how much data you put in this delta.
Thanks. This is very interesting. More questions or comments? From Zoom, is there any question or comment? If not, let's thanks again the speakers for the excellent presentation and discussion.
Thanks a lot. Have a nice day.
Okay, thank you very much. Thank you.